Polypropylene, sometimes referred to as polypropylene, is a popular thermoplastic polymer widely found in numerous products. Manufactured from the polymerization of propylene molecules, it falls under the broader category of polyolefins and displays partial crystallinity alongside a nonpolar character. Its features closely recall those of polyethylene. However, polypropylene presents slightly greater surface hardness and resists higher temperatures before deforming. Commonly appearing white and noted for its sturdy build, it remains highly stable even when exposed to many chemicals. Polypropylene ranks just behind polyethylene in terms of global plastic production volume. The material maintains flexibility and is considered tough, especially when ethylene is incorporated to form a copolymer, which further broadens its usability. Polypropylene's melting behavior does not occur at a fixed point, but over a narrow temperature range, primarily identified through thermal measurement techniques. The melting point depends on the degree of crystallinity and the presence of regions formed with different tacticities. Perfectly isotactic varieties show higher melting points, whereas copolymers and amorphous forms melt at somewhat lower temperatures. Upon reaching sub-zero temperatures, polypropylene may become brittle. Chemically, propylene molecules usually attach to one another in a particular orientation, but with some misalignment, leading to polymer chains where methyl groups don't always follow a strict order. At room temperature, polypropylene stands up to most organic solvents and is a good choice for storing acids and bases. However, when heated, it can dissolve in select nonpolar solvents. The material's molecular structure leaves it ever so slightly more susceptible to chemical attack than polyethylene due to the presence of tertiary carbon atoms. Polypropylene is manufactured in several forms, including pure homopolymers and copolymers with small amounts of ethylene or other comonomers. Copolymers with randomly introduced ethylene units become more transparent, whereas the addition of rubber-like components improves properties at lower temperatures. The concept of tacticity plays a fundamental role in properties, with isotactic, atactic, and syndiotactic forms exhibiting very different behaviors. Commercial polypropylene tends to be primarily isotactic, meaning its chains are arranged in a consistent helical manner, contributing to higher crystallinity and thus increased stiffness, melting point, and hardness. While isotactic polypropylene is partly crystalline, syndiotactic versions exhibit lower crystallinity, and atactic types remain amorphous, unable to form crystals and operating as a sticky, rubbery material at room temperature. Crystalline structures within isotactic polypropylene include several forms, with the so-called alpha form most prevalent. The arrangement of long polymer chains within these crystals can have unique features, such as a cross-hatched pattern, and leads to melting points and densities that vary depending on the specific structure and processing conditions. Some crystallinity modifications are encouraged through specific processing methods or additives. Atactic polypropylene, due to its lack of regular structure, does not crystallize and is often separated as a byproduct during isotactic polypropylene production, though it is useful as a sealant or insulating material. Variants with more carefully controlled production processes achieve different molecular weights and properties. There is also significant interest in copolymers, such as random copolymers blending in ethylene, which see use in plumbing and pipework due to their improved transparency and toughness. Newer forms are optimized to resist higher temperatures thanks to greater proportions of certain crystalline forms. Polypropylene is vulnerable to breakdown through exposure to heat or ultraviolet light, which can cause the main chains to break down, resulting in surface cracking. Protective measures can be taken through the use of certain stabilizing additives. Research has shown some microbes may be capable of degrading polypropylene under specific conditions, and medical devices made from polypropylene occasionally exhibit distinctive surface changes due to material degradation in the body. Optically, uncolored polypropylene appears translucent, but is generally less transparent than other plastic types. Polypropylene forms through polymerizing propene using various industrial methods, primarily gas phase and bulk processes. In gas phase systems, propene flows over a bed of solid catalyst. The resulting polymer gathers as a fine powder, later turned into pellets while unreacted gases are collected and recirculated. Bulk polymerization relies on liquid propane as the medium, maintaining specific conditions to hold the monomer in that state, and often utilizes loop reactors. This method restricts the amount of ethene as a comonomer because of limited polymer solubility in liquid propene. In slurry polymerization, inert alkanes suspend growing polymer particles while propene enters as a gas. Polypropylene's properties depend greatly on tacticity, the spatial arrangement of methyl groups in the polymer chain. Ziegler-Natta catalysts, using TiCO4 supported on MgCl2 and organic modifiers, enable the creation of isotactic polypropylene where methyl groups align on the same side, giving the polymer desirable mechanical characteristics. These catalysts are activated by organoaluminium co-catalysts. The details of catalyst preparation, especially the support and modifiers, determine productivity and the nature of the resulting polymer. Syndiotactic polypropylene, where the arrangement of methyl groups alternates, is synthesized using specialized metallocene complexes which are activated by methylaluminoxane. Polypropylene is commonly melted in extrusion and molding operations. Techniques include producing melt-blown or spun-bond fibers for items like wipes and masks, while injection molding shapes products such as containers, utensils, and automotive parts. Modifications during manufacturing, such as adding anti-static agents or tailored additives, permit a wide array of uses. Surface treatments enhance adhesion for printing and painting. Expanded polypropylene EPP is made by manipulating crystalline structures or blending polypropylene with other polymers to aid expansion, since its crystalline nature resists conventional foaming techniques. Biaxially oriented polypropylene, BOPP, is made by stretching film in two directions to improve strength and clarity, lending versatility for packaging, labeling, and various industrial needs. The breadth of polypropylene applications comes from its resilience and modifiability. Its resistance to fatigue allows production of living hinges on packaging. In plumbing, polypropylene is used for its durability, inertness, and thermal fusion joining capabilities. Its resistance to high heat enables use in autoclaves, kettles, and dishwasher-safe containers, with lids often made from more flexible materials for ease of closure. Laboratory ware, medical devices, bottles, pails, automotive batteries, and numerous household goods feature polypropylene because of its adaptability and cost-effectiveness. For fibers and films, polypropylene serves in ropes, insulation, carpets, filters, and protective membranes. Its buoyancy makes it popular for marine ropes, and it is widely applied in electrical cable insulation, particularly where non-toxicity is required under fire risk. Polypropylene films are cut to size for packaging or used as clear, flexible sheets for design and stationery products. Designers exploit its lightweight and vivid colors for products like lampshades. It also provides reinforcement in construction. Fibers can strengthen concrete or soil for earthquake-prone regions. As a textile, polypropylene finds use in diapers, sanitary products, and base layer clothing with moisture-wicking qualities, sometimes replaced by polyester in more recent applications due to odor retention issues. Mechanical recycling of polypropylene is limited, with most still not collected for reuse, partly because its carbon-methyl backbone is more susceptible to degradation when heated than polyethylene. Objects made from polypropylene can be repaired or joined using adhesives or welding equipment that heats and fuses the material at the joint. Polypropylene is assigned the recycling code 5.